Hi everyone. So today we're going to continue Math 103, Lecture 22. Math 103. So our last time we considered series, infinite series, and this is what we did. So just a quick recap of Lecture 22. So given a sequence, a sub n, we considered the series that you get out of this sequence, which was sigma sum n goes from 1 to infinity of a sub n. And what this means is just adding up all the terms of the sequence. And how did we define the infinite series precisely? Well, we defined it through something called a sequence of partial sums. So the sequence of partial sums was defined to be partial sums was S sub n, where S1 is just a sum of the first term, S2 is sum of the first two terms, and S3 is sum of the first three terms, so on. And so we see that S sub n is sum of the first n terms. So I goes from 1 to n of a sub I. And so we've constructed sort of a new sequence, and we can consider a convergence of this sequence S sub n. So if the sequence S sub n, where n is at least 1, converges, then we say that the infinite series converges. Then we say that the corresponding series converges. And this should make sense intuitively, because what are S sub n's? They're just adding up the first n terms of this infinite series. And so as you let n here get larger and larger, you're adding up more and more terms. So S sub million is adding up the first million terms. So it makes sense that if the Sn's themselves converge, namely, if the values of Sn gets closer and closer to a particular value, that it makes sense that that should be a good approximation for the infinite series, summing up all the terms at once. And in fact, in this case, so if Sn converges, not only we say that the series converges, moreover, the value of the infinite sum, the value of the infinite series, n goes from 1 to infinity of an, must be just the limit as n goes to infinity of Sn. As you add more and more terms, namely by as you add up more and more terms, namely by letting n go to infinity, you will get the sum of all the terms. That's the gist of sequence of partial sums. Of course, there's also the possibility that the sequence Sn does not converge. So if the sequence S sub n, sequence of partial sums, diverges, then we say that the corresponding series also diverges. Okay. So we also discussed the divergence test. So just a quick recap of what divergence test says. It says the following: if the limit as n goes to infinity of a sub n, if the limit of the nth terms, so an is also known as the nth term, because this is the nth term of the sequence. So if the limit of the an's is not 0, then the infinite series diverges. right? So this makes sense because for us to have a hope of adding infinitely many terms and for having and converging, we must have that the limit of the ands must be 0, because we keep adding more and more terms, right? So how could this sum converge? Well, if it were to converge, then the ands should get smaller and smaller. They should converge towards 0. So if we know that the limit of the ands is not 0, then we can automatically conclude that the series must diverge. And so notice that this condition also includes the case when the limit does not exist. The limit of the ands does not exist. So it's even better. So if the limit of the ands does not exist, well, then certainly it's not 0, in which case we can conclude that the limit of the ands diverges. Okay, so one big warning is that if the limit of the ands is 0, then we can't say anything. We simply cannot conclude anything from the divergence test. So warning. So this is a very, very common mistake people make in the exams, which is that they apply divergence test incorrectly. So if the limit of the ands is 0, then sometimes I've seen this mistake a lot. The students say, well, if the limit of the ands is 0, then the series must converge. That's not what the divergence test says. It just says that if the limit of the ands is not 0, it's not 0, then the sum of the ands diverges. But if the limit of the ands is equal to 0, then we cannot deduce anything from the divergence test. Then we cannot deduce. So I can't emphasize this enough. So maybe I'll write in red. We cannot conclude anything about the convergence of the series. About the convergence of the infinite series sum n goes from 1 to infinity of a sub n. Meaning that like anything could happen. We need to use some other tests to figure out what's going on with this series. Whether this series converges or diverges, we need some other tests. The divergence test is useless. And in fact, we have seen examples last lecture where, for example, we looked at n goes from 1 to infinity of 1 over n, right? So in this case, a sub n is 1 over n, and certainly a sub n converge towards 0. But this series diverges. We also saw an example with this example, 1 over n squared. And here, an, the nth term, is 1 over n squared. And of course, the limit here is also 0. The limit of the an's, limit of 1 over n squared as n goes to infinity is 0. But this example, the sum, 1 goes from 1 to infinity of 1 over n squared converges. So you see, anything can happen. If the limit of the an's is 0, right, in this both examples, let me just rewrite it again. Limit of the an's is 0. Here also the limit of the an's is 0. Anything can happen. The series could diverge or the series could converge, so we cannot possibly apply the divergence test. So once again, the divergence test says if the limit of the an's is not 0, then the sum as n goes from 1 to infinity of an must diverge. And also, it's in the name, divergence test. Divergence test can only be successfully used to prove divergence. If you prove convergence of a series with divergence test, then you know you're wrong, because divergence test can never prove any type of convergence of a series. Okay, so this was just a recap of what we did in lecture 21. And so actually, I'll just give a quick example of how to apply. So example, how to apply divergence test. So let's look at this series. Sum n goes from 1 to infinity of n divided by square root of n squared plus 17. So let's find out if this infinite series converges or diverges, or diverges. Okay, so we should apply the nth term test. That's sort of the first test you can always apply because it's relatively straightforward to apply. So to apply divergence test, we have to find out what's the nth term. The nth term that we're adding. Well, this is always the thing in front of the sigma. So a sub n in this case is n divided by n squared plus 17. Now, what we have to do is compute the limit of the an's. So need to compute the limit of the an's and see what happens. Okay, well, let's see. So we have limit as n goes to infinity of a sub n is limit as n goes to infinity of n divided by square root of n squared plus 17. So the trick here is the following. So if you look at the leading order here is at the top, it's just n, so it's just n to the power of 1. At the bottom, the leading term is actually also n, because it's n squared, but then there's a square root. So this suggests that the leading term in the denominator overall is n to the power of 1. So since both of them are n to the power of 1, the ratio should be 1. So I expect the limit of the an's should probably be 1, so we can prove it. And the way we're going to do it is we're going to multiply top and bottom with 1 over n. So I'm going to multiply top and bottom with 1 over n, right in blue. And so I have not changed the fraction when I do this. So I'm just multiplying it with 1 over n. Okay, so what happens? Well, the top, n times 1 over n becomes 1. Now to simplify the denominator, let me pull 1 over n inside the square root. So I have n squared plus 17. Well, if you pull 1 over n inside the square root, it has to go inside as a square. So it has to go inside as 1 over n squared. Because when you take the square root of 1 over n squared, it does become 1 over n, which is what we have here. So every time you want to move stuff inside the square root, you can do it as long as you square it in the inside. And so we get limit as n goes to infinity of 1 divided by square root of, so this is just n squared divided by n squared plus 17 divided by n squared. So we get limit as n goes to infinity of 1 over, so now our fraction will become simpler. So n squared divided by n squared is just 1. So 1 plus 17 over n squared. So now this part will go to 0 as n goes to infinity. Because it's 17 divided by n squared, so as n gets larger and large, you're dividing by a bigger and bigger number. So this term sort of dies out, the limit. So the answer is 1 divided by square root of, this 1 remains the same because it doesn't depend on n. And you get 1 plus 0 for this. And now I no longer have a limit. And so this becomes 1 divided by square root of 1. So this is 1 divided by 1, which is 1. And notice 1 is not 0. Okay? So what we have shown, let's go look back. We have shown that the limit of the an's is not 0. It's equal to 1. So it's not 0. That's all we care about. Since the limit of the an's is not 0, we can apply the divergence test. It's not 0. We apply the divergence test to conclude that the series must diverge. the corresponding series, which was n divided by square root of n squared plus 17, diverges. Okay, so next topic. Well, let's review a telescoping series using an example. But before we do that, maybe we can ask a question. Can we apply divergence test successfully to the series sum n goes from 1 to infinity of 1 divided by n times n plus 3. And, well, in this case, an, so answer, in this case, an is 1 divided by n times n plus 3. Note that the limit of the an's, in this case, is just 0, because you're taking a limit of the expression 1 divided by n times n plus 3. So as n gets large, the denominator gets larger and large. So in the limit, this ratio is 0. Okay, but if the limit of the an's is 0, the divergence test cannot be applied. Divergence test cannot be applied. Okay, so divergence test can only be applied if the limit of the an's is not 0. If the limit of the an's is 0, we just cannot say anything. Okay. So for all we know, this series could diverge or converge. So for all we know, change the ink. This series, this infinite series, could diverge or converge. We just don't know just by looking at the nth term test. Just by looking at the divergence test, I mean, we cannot know. So we need other tools. So let's actually work on this example. So I'm going to try to illustrate the method of telescoping sums using this example. But before we do that, maybe we can simplify the sum by using a partial fraction decomposition, right? So let's try to understand the sum in more detail. Try to understand. So we're going to use partial fraction decomposition as the first step. So we have sum n goes from 1 to infinity of 1 divided by n times n plus 3 in more detail. So if we use partial fraction decomposition, we can try to split this 1 divided by n times n plus 3 into a divided by n plus b divided by n for some, b divided by n plus 3 for some constants a and b that we have to find. And the process for this one is you make a common denominator. So on this side, we have 1 divided by n times n plus 3, and on this side, we make a common denominator, n times n plus 3. So for this term, I have to multiply the denominator with n plus 3, which means I have to multiply the numerator also with n plus 3. And for this term, to make a common denominator, I have to multiply n plus 3 with n, which means I have to multiply the numerator b with n as well. So I get this. So, and I can clear the denominator, and so I get that 1 should equal to a times n plus 3 plus b times n. Now to solve for a and b, I just have to plug in judicious choices of n. So if you plug in n equals to 0, that's going to give you 1 equals to a times 0 plus 3 plus b times 0, and b times 0 is just 0. That's good. So that tells me a times 3. That gives me 3a. So 3a is equal to 1. 3a is equal to 1 means a is equal to 1/3. And similarly, if you plug in n equals to minus 3, you're going to get 1 is equal to a times minus 3 plus 3 plus b times minus 3. And so this term is just 0, and this gives me minus 3b. So I get minus 3b equals to 1. So I get this. And so this tells me that b must equal to negative 1/3. Okay, so we found a and b. So let's go back. So we have a is equal to positive third and b is equal to negative third. That tells me that 1 over n times n plus 1, n plus 3, is equal to a divided by n, so 1/3 divided by n, plus b divided by n plus 3, so negative 1/3 plus n plus, divided by n plus 3. So I can actually factor out 1/3. So I get 1 over n, let's see, and then plus 1 over n plus 3. Okay. So then the sum that I'm interested in, which was this one, ends up being sum as n goes from 1 to infinity of 1/3 times 1 over n plus 1 over n plus 3. So somehow I made a sign mistake, so it should be minus. It should be minus. Okay, so somehow I claim that this is going to be easier to deal with. So what we're going to do is we're going to compute the sequence of partial sums. So sequence of partial sums will be easier to compute for this expression compared to this one. Sequence of partial sums. So this is s sub n as n goes from 1 to infinity. So let me just write down what is s1. So s1 is the first term, because you're summing only the first term. So this is the case when you plug in n equals to 1 into this expression. So you just get 1/3 times, well, if you plug in n equals to 1, you get 1 over 1 minus 1 over 1 plus 3. So that gives you a 4 here. Okay, that's the first term. So now, next, S2 is the sum of the first two terms. So I have the first term, which I have already written above, but I also have to now add the second term. Okay? So the second term is 1/3 times, it's when you plug in n equals to 2 into here. So I get 1/2 minus 1 over 2 plus 3, which is 5. So it gives me 1/2 minus 1/5. Okay, so far there's no cancellations, but we have to keep going a lot. So in fact, I'm going to zoom out a little bit so we can actually, I'm going to try to do, up to 6, 7 actual terms to see what's going on. I mean, it's one of these cases where to see the pattern, you really have to write down a lot of terms. So S3 is the sum of the first. So let me write, so maybe I can write down the sum we're interested in here so we don't forget. So the sum we're interested in is as n goes from 1 to infinity of 1/3 times 1 over n minus 1 over n plus 3. So this is the sum for which we're computing the sequence of partial sums. So S3 is the sum of the first three terms of this sequence. So that's when you basically just plug in n equals to 1, and then you plug in n equals to 2, and then you plug in n equals to 3, and you just add them up. So the first term is this one. The second term is when n is equal to 2, is this one. Finally, the new term, when you plug in n equals to 3, is 1/3 minus 1/5. So there's always going to be a factor of 1/3 in front because of this 1/3. So S4 is the sum of the first 4 terms. Just get this. Half plus 1/3. And now I have to add the fourth term. So that's 1 over 4, because that's what happens when you plug in n equals to 4. And then you plug in n equals 4 here, so you get minus 1 over 7. Okay, S5 is 1/3 minus 1/2 plus 1/4 plus 1/3, half minus 1/5 minus 1/5. Sorry, I think I made a little typo here. I'm sorry. This should be 6, not 5. So 6. I get 1/3, 1/4 minus 1/7, and then I have 1/3. Now I have to plug in n equals to 5 because I'm adding up the first 5 terms. So I just get 1/5 minus 1/8. Okay. Let's go for S6 and S7. So S6 is 1/3. So I can just copy down what I have for S5 and just add the last term, which is add the 6th term. So I just do that. That's 1/3. 8, and now I had to add the 6th term, so that's 1/3 times 1/6 minus 1/9. That's what happens when you plug in n equals to 6. Okay, so I have to zoom out a little bit more to be able to write down the 7th term. So I have S7, so that's going to be, this is going to be the last one I'm going to write down. So the reason I'm writing all this down is because now we're going to see what kind of cancellations happen. And from there on, we're going to see the pattern. And once we see what the pattern is, we'll be able to write down the nth term for any n. And from there on, we'll be able to compute the limit of the SNs. We'll be able to compute the limit of the partial sums, which is what we need in order to compute the limit of the series, in order to compute the sum of the infinite series. So, okay, so I'm almost done. So I have n equals the 6th term, and finally, because I'm looking at S7, I'm going to compute, I'm going to add one more term, which is the 7th term, 1/7 divided by 1/10. Okay, so now let's look at what happens here. What kind of cancellations do we have? So I'm going to write down the cancellations in red. So let's see. Okay, so S1, I don't see any cancellations. S2, I don't see any cancellations. S3, I don't see any cancellations. Somehow, like, these are too small of values to see anything. So I start seeing stuff happen starting at S4. So at S4, let's see. So I see that this negative 1/4 here, negative 1/4, canceled with the positive 1/4. So I can just get rid of these, right? They both have 1/3 in it, so it doesn't matter. So 1/3 times 1/4 canceled with 1/3 times 1/4 because it comes with a negative sign here, comes with a positive sign here. Now the rest of the terms you really can't do anything, it's just there. S5, again, this quarter is going to get canceled out with this quarter, but now we're seeing something more. Negative 1/5 is going to actually get canceled out with this negative, with positive 1/5 here. Now in S6, again, I have the quarters getting canceled and 1/5 getting canceled. But also negative 1/6 is now going to get canceled with this positive 1/6. Right? Now what's happening? Let's look at S7. So again, negative 1/4 is going to cancel out with the positive 1/4. Negative 1/5 is going to get canceled with the positive 1/5. Negative 1/6 is going to get canceled out with the positive 1/6. Sorry, I copied something wrong again. This should be 8. So this number is always 3 more than this number. Okay, so 1/4 canceled with 1/4, negative 1/5 canceled out with negative 1/5, negative 1/6 canceled out with negative 1/6. Now we see that even negative 1/7 gets canceled with 1/7, and you just get the rest of the terms. Now, what is one thing that we observe? Well, we observe that the terms of 1/1, 1/2, and 1/3, they never get canceled. There's never going to be a case where something is going to cancel out with 1/1, 1/2, and 1/3. So they survive. And then the rest will eventually get canceled, except there's always going to be these 3 terms that survive at the end, like these. And so, what does that tell us? that tells us the pattern is the following. Basically, Sn, for any n, is just 1/3 times, so 1/1 gets survived, so this is 1. 1/2 gets survived, so it's a plus half. So I've just pulled out 1/3 from all the terms. And then 1/3 gets survived. This 1/3, this 1/3 gets survived. And then I also have some negative terms that survive near the end. And what are they? Well, they're just the tail, the last 3 terms. So they're negative m plus 1 minus m plus 2 and minus m plus 3. Like you can see this from 7, right? Let's look at S sub 7. What survives is 8. Negative 1/8 survives, negative 1/9 survives, negative 1/10 survives. So that's exactly m plus 1 coming from. So if it's n here, it's m plus 1, m plus 2, and m plus 3. And of course, the initial terms survive. So once you have this, then you can compute the limit already. So the limit as n goes to infinity of Sn's is just the limit as n goes to infinity of this expression here. So this is 1/3. That's 1 minus 1/2 plus 1/2 plus 1/3 minus 1/m plus 1 minus 1/m plus 2 minus 1/m plus 3. Now each of these, they will go to 0. They will go to 0 as n goes to infinity because you're dividing by a bigger and bigger number. And so in the limit, you just get 1/3 times 1 plus 1/2 plus 1/3, which we can simplify as follows by making the common denominator of 6. So this is 6. So this 1/2 becomes 3/6. 1/3 becomes 2/6. So this tells me I get 1/3 times 6 plus 3 is 9 plus 2 is 11. So I get 11/6. So I get 11/18. So what we have seen is that the limit of the Sn's converge. So since the sequence of partial sums converge, we conclude that the series must also converge. Converges. We conclude that the series n goes from 1 to infinity of 1/n times m plus 3 also converges. And moreover, we've actually figured out the value of this infinite sum. Moreover, the sum is equal to, by definition, is equal to the limit of the partial sums. Limit for the sequence of partial sums. So this is just 11/18 because we computed the limit of the partial sums. Limit of the Sn's is 11/18. So in fact, that's what the infinite series is equal to. Great. Let me just zoom back. So next, I want to discuss a new test called the ratio test. This is an extremely powerful tool to compute, to determine whether a given series converges or diverges. So given an infinite series, sum as n goes from 1 to infinity of an, we will consider the following quantity. The limit, we'll consider the quantity, which is the limit of n goes to infinity of absolute value of am plus 1 divided by an. Right? Somehow this is the key quantity to consider, and that's why it's called a ratio test, because you're comparing, you're trying to compute the ratio of consecutive terms. So a sub n is the nth term, and a sub n plus 1 is the n plus 1th term. And so what you're doing is you're just dividing them, so computing their consecutive ratio, and trying to understand where does that tend to, if it has a limit, and what is the limit. Now, so what is the actual statement of the ratio test? It has a couple of parts. The first part is that if this limit exists and is less than 1, then the series converges. Then the series converges. Okay, the second part is that if this limit exists but bigger than 1, then the series diverges. If this limit, as n goes to infinity, of absolute value of an plus 1 divided by an is bigger than 1, then the series actually diverges. Okay, well, what about the case when the limit is equal to 1? Well, in this case, the test is inconclusive, meaning that it's useless. Anything could happen. We need more tests. We need further tools. So if the limit of the as n goes to infinity of the absolute value of an plus 1 divided by an is 1, then the test, the ratio test, is inconclusive. Inconclusive means it's simply not helpful. And so in particular, anything can happen. The series could converge or diverge. We just don't know. Well, of course, there's actually one more case, which if this limit doesn't even exist, right? If this limit goes to infinity of an plus 1 over an does not exist. In this case also, we can't say anything. If it does not exist, then again, the ratio test is inconclusive. So I'm not going to give a proof of ratio test. If you are interested, you can read the book. And the basic idea is that you compare it to a geometric series. But if you just look at the statements, I think it's convincing or believable that under this condition, under the first condition, it should converge. Because what this is saying is that the ratio of consecutive terms are getting, well, they're less than 1, which means the an, the n plus 1 term is getting much, much smaller than the nth term, because the ratio is smaller than 1. That makes kind of, it's believable that that would imply that the series converges, because the terms are getting much, much smaller compared to each other. On the other hand, for part 2, if the limit of if this limit is bigger than 1, this means that an plus 1 is bigger than an. So the terms are getting larger and larger, and so there's no way that the series could converge, because the terms are getting larger. And and oftentimes in interesting cases, you might run into part 3, where the limit of the ans is 1. Sorry, not of the limit of the ans, but limit of this quantity, an plus 1 divided by an, this is 1, then we simply have to use other tools. Same with this case. So let me show you how we apply ratio test in practice. So here's an example. So let's determine whether the following series. So this is sum as n goes from 1 to infinity of 100 to the power of n divided by n factorial converges or diverges. You have to figure it out. Okay, so solution is going to use the ratio test. Let's apply the ratio test. So an in this case is 100 to the power of n divided by n factorial. So you compute the limit as n goes to infinity of the absolute value of an plus 1 divided by an. And so this is the limit as n goes to infinity of, okay, so what is an plus 1? That's n plus 1 is the same thing as an, except every time you see n, you replace it with n plus 1. So an plus 1 is 100 to the power of m plus 1 divided by m plus 1 factorial. And then I'm going to divide that thing with an. So an is 100 to the power of n divided by n factorial. Now, if you divide two fractions, what you get is you have to flip the fraction at the bottom. So what we get is limit as n goes to infinity of the absolute value of 100 to the power of m plus 1 divided by m plus 1 factorial, and the fraction at the bottom gets flipped. So I just get n factorial divided by 100 to the power of n. Now, everything here is positive, so we can just get rid of the absolute values and simplify as follows. So 100 to the power of n is the same thing as 100 times 100 to the power of n. n plus 1 factorial, this is just n plus 1 times n minus 1 up to 1. So it's the product of the numbers from 1 to n plus 1. That's the same thing as n plus 1 times n factorial, right? Because n plus 1 times n factorial is precisely the product of the numbers from 1 to n plus 1. Because the product of the numbers from 1 to n is already kind of packaged here, and so I'm just multiplying with an additional n plus 1. So n plus 1 factorial is equal to n plus 1 times n factorial. It's a very, very useful fact. So it's so useful that I'm going to write it in blue here. So we use this fact. And if you're not convinced, you should try to think about it. n plus 1 times n factorial. This fact was very useful. Okay, this is a useful fact. And times n factorial divided by 100 power of n, and so some cancellations happen. So 100 to the n gets canceled out with this 100 to the n factorial gets canceled out with this n factorial. And so what we end up getting is, we just end up getting limit as n goes to infinity of 100 divided by n plus 1. Well, as n gets larger and larger, this 100 is not going to be able to do anything. This n plus 1 is going to grow larger and large, so this ratio is going to tend to 0, which is less than 1, and that's what we care about. So we've shown that the limit that appears in the ratio test, namely the ratio of n plus 1th term to the nth term, in absolute value, the limit of that we have shown is equal to 0, which is less than 1. So if we go back to the statement of the ratio test, we're in case 1. So it's less than, this limit is less than 1. So we conclude that the series converges. So we conclude that the series n goes from 1 to infinity of 100 to the power of n divided by n factorial converges. This is by the ratio test. Okay, so I'm going to give another example. So slightly more involved, and also using factorials. So in general, like if you see a factorial, it's a good sign that the ratio test will be helpful. It's kind of a tip right there. If you see factorials, ratio test might be helpful. To apply. So here's an example. Okay. So determine convergence / divergence of the following series. So n goes from 1 to infinity, and I have the following ratio. So here I have 3n factorial at the top. At the bottom, I have n factorial times n factorial times n factorial. So let's apply the ratio test. So in this case, our series is of the form sum n goes from 1 to infinity of an. So what we care about is an. So an is the thing in front of the sigma, is 3n all factorial divided by n factorial times n factorial times n factorial. Now, because we're going to be applying the ratio test, we're going to have to deal with a of n plus 1, a sub n plus 1, right? Because we have to deal with this ratio. So we need to compute a of n plus 1. So let me just compute that on the side, because we're going to need it. So, a sub n plus 1 is exactly the same thing as a sub n, except that every time you see n in the formula, every time you see n, you need to replace it with n plus 1. So for the numerator, I have 3 times, so instead of 3n, in the parentheses, I have 3 times m plus 1, and I take the factorial of that. I have to divide that by, and I have to divide this by n factorial times n factorial times n factorial. I have to replace it with n plus 1, right? Sorry. So times n plus 1 factorial times n plus 1 factorial times n plus 1 factorial. Right, that's the whole point. Every time I see n, I replace it with n plus 1. So now, the key is how are we going to simplify this? Well, it will help if we write the numerator as follows. So it's 3 times n plus 1 factorial. So it's the same thing as 3n plus 3. After I just FOILed this 3 inside, I get 3n plus 3 because it's 3n plus 3 times 1. And then I take a factorial. And at the bottom, I have n plus 1 factorial times n plus 1 factorial times n plus 1 factorial. Okay. We're going to have to take the ratio of an plus 1 divided by an, right? So we'll have to somehow get cancellations. So to do that, let's just actually start doing the ratio test. So we need to compute the limit as n goes to infinity of absolute value of an plus 1 divided by an. So I have limit as n goes to infinity of, so let me write down an plus 1 first. So an plus 1 is the following. So I have 3n plus 3 factorial divided by n plus 1 factorial n plus 1 factorial times n plus 1 factorial. So there's times in between. And then I have to also, so this part is just a sub n plus 1. Now I have to divide it with a, you have to divide this by a sub n, right? So I have to divide this whole thing. Somehow I have to divide this whole thing. Let me write this a little better. So I have to divide this whole thing with a sub n. So a sub n is this thing. 3n factorial divided by n factorial times n factorial times n factorial. So this is the ratio we need to consider. Now, again, when you divide two fractions, what you can do is you take the fraction, you take the term in the numerator, keep it as it is, and then you multiply it with the flipped version of the denominator. So what you end up getting is the following. So you get limit as n goes to infinity of absolute values. So at the top we had 3n plus 3 factorial divided by n plus 1 factorial times n plus 1 factorial times n plus 1 factorial. And then at the top I have the flipped version. I have the flip version of this thing. So I have n factorial, I have n factorial times n factorial times n factorial. And at the bottom I have 3n factorial, like so. Okay, well, the thing is, I have to be able to cancel stuff. Otherwise, there's no hope I can compute this limit. So here's the observation. And so first of all, I can drop all the absolute values because everything in sight is positive. And what about 3n plus 3 factorial? Well, this is just 3n plus 3, right, times 3n plus 2. I just keep going down by 1, and 3n plus 1. And then I'm going to have 3n times 3n minus 1, and dot, 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 all the way up to 1. But I can just repackage the rest of the terms as 3n factorial, right? This expression right here is exactly the product of the numbers from 1 to 3n plus 3. And I've just written it backwards, right? So I've started at the top term, 3n plus 3, times next term, 3n plus 2, times the next term, 3n plus 1, times, and the rest of the terms is just 3n factorial, the product of the numbers from 1 to 3n. So this is a useful trick, being able to rewrite this factorial as as a product of 3 terms plus another factorial is going to be helpful, because it's going to help us cancel with this 3n factorial. And similarly, m plus 1 factorial, as we've seen earlier in the earlier example, m plus 1 factorial is the same thing as m plus 1 times n factorial. So there's 3 of these. So m plus 1 factorial in the middle is m plus 1 times n factorial. Again, this last m plus 1 factorial is m plus 1 times n factorial. And I'm multiplying this with n factorial times n factorial times n factorial. And I'm dividing this thing by 3n factorial. Okay, so now we see lots of cancellations happening. So first of all, this 3n factorial cancels out with this 3n factorial. And then n factorial cancels out with this n factorial. Oops, sorry, something crazy happened. I have to undo. And then, okay, so this n factorial cancels out. Okay, so this n factorial cancels out with this n factorial cancels out with this n factorial, and this one cancels out with this one. So what do we end up getting? Well, we end up getting limit n goes to infinity of 3m plus 3 times 3m plus 2 times 3m plus 1 at the top. And at the bottom, what has survived is m plus 1 times m plus 1 times m plus 1. So it's a ratio of two actually polynomials of degree 3. So I can just analyze the leading term behavior. So this is limit as n goes to infinity of, well, the leading term here is going to come from multiplying the 3n with this 3n and with this 3n, and that's going to give you 27n cubed. And then you're going to have here lower order terms. Maybe I can write it. So here you're going to have lower order terms. Terms involving, n square, n, and constant term. At the bottom, the leading term is multiplying n with n. That's going to be n cubed, plus again, lower order terms. Terms that basically don't matter for computing the limit as n goes to infinity. And the way you compute this is just ignore the lower order terms and compute the ratio of the leading terms. So I have 27 times n cubed here, and here I have invisible 1 times n cubed. So the answer is just 27 divided by 1. So this is 27. So what did we just show? If you go back, we just showed that the limit as n goes to infinity of the absolute value of am plus 1 divided by an is 27. So which is bigger than 1? So we showed that the limit as n goes to infinity of am plus 1 divided by an is 27. In particular, it's bigger than 1, so we can apply the ratio test to conclude that the series must diverge. By the ratio test, the series n goes from 1 to infinity of 1 to infinity of 3n factorial divided by n factorial times n factorial times n factorial diverges. Great. So next test we want to discuss is called the integral test. And this is a very powerful method which sometimes works to determine if the series converges or diverges. So here's a setup. So suppose the infinite series we have is of the following form. Infinite series we have is of the form, so I have a sum, n goes from 1 to infinity. Doesn't start from 1, it could start, it's more general. It could start from any number a of f of n, so where f is some function. Right, so what I'm saying is that the nth term of my series is of the form f of n, where f is some function. Well, what is f? F of x is some function satisfying some conditions. So, is a function. Well, it's a continuous function, so we'll be able, because we'll need to integrate the function later. So, it's a continuous function on the interval a to infinity, such that so actually I want it to be continuous on the closed interval, so also be okay around a. So f of x is a continuous function on this interval such that two conditions must hold. Okay, so these are two important conditions. So f of x has to be positive on this interval, and f of x should be monotonically decreasing. These are the two conditions that you need before you can apply the integral test. So these are the sort of hypotheses of the integral test. If you don't have these conditions, then you cannot apply integral tests. So, so this is one of the conditions, and this is the other condition. Okay, so then what does the integral test say? So integral test says that then the integral test states the following. Test states the following. So the sum, n goes from 1 to infinity, of f of n converges if and only if the integral, the corresponding integral, this should not be 1, should be any starting point a, if and only if the improper integral from a to infinity of f of x dx converges. So this is what the test says. Now, this is an extremely useful technique because it's saying that the series and the integral have the same behavior. And this is what if and only if means. If and only if means that if this statement is true, that is, if the sum as n goes from a to infinity of f of n converges, then this statement is also true. The integral must also converge. Similarly, if the integral converges, then the sum must converge. So if and only if basically means that these two statements, this one here and this one here, they have the same truth value. So if this converges, then if the series converges, then the integral converges. If the integral converges, then this series converges. So, which of course implies that if the series diverges, then the integral must diverge, and if the integral diverges, then the series must diverge. Basically, in short, the series and the integral have the same convergence property. And this is useful because sometimes the series is much harder to figure out, so we can just pass to the integral, where it's easier to figure out if the integral converges. So before I give examples, I would like to justify why should we believe this result. Why is it that the convergence of a series is determined by a convergence of an integral? And I'm going to actually prove prove to you why this is true by doing the following. So the integral test follows from the following inequality. So integral from a to infinity of f of x dx is at most the sum, n goes from 1 to infinity of f of n, and it's less than or equal to f of a plus integral from a to infinity of f of x dx. So we have kind of two inequalities we have to justify, 1 and 2. Okay, so before I go on with proving why 1 and 2 is true, which I'm going to show by drawing a picture, it's going to be very similar to Riemann sums. But before I do that, let's understand why knowing this chain of inequalities tells us the result we want. Well, here we see that the integral, so here we see that the series is squeezed between the integral and the integral itself, except there's an additional term here, right? So if the series converges, then certainly the integral must converge, because the integral is smaller than the series, right? And we also know, of course, that everything is positive. Everything is positive because f is a positive function, right? F is a positive function. So certainly, if we know that the series converges, then the integral is smaller than something that converges, so it must converge. Similarly, if we know that the integral converges here, then we know that, well, this thing also converges because it's just the integral plus f of a, then the series must also converge because it's smaller than it. So that shows that they have the same convergence and divergence behavior. So how do we prove this inequality 1 and inequality 2? So let me draw a picture. So let's try to draw a graph of f. So this is my y-axis. This is my y-axis, and this is my x-axis. So I'm going to draw the picture of a graph. And I know the function is monotonically decreasing, so it looks something like this. So this is the graph of f of x. And I'm going to plot a, that's the starting point. This is a, and then I have, try to draw a little better. So I have a here in the beginning, and I have a plus 1, then I have a plus 2, then I have a plus 3, and so on. Okay. So let's look at these rectangles here. So I'm going to draw, I guess this is the right endpoint Riemann sum. Okay, so now notice that the sum of the areas of the rectangles is an overestimate for the area under the curve. So, what are the areas of these rectangles? Like, what are the areas of these rectangles? So this one here is, well, all the widths are just 1, right? The widths are just 1. So the area is just determined by the height of the rectangle, and the height of the first rectangle is f of a. Height of the second rectangle is f of a plus 1, and so on. So we see that the sum of the areas of the rectangles in the picture on the right, on the left of the screen, is simply, what is it? It's well, it's f of a, because that's the area of the first rectangle. It's just the height, f of a. The width is 1, as I said, so it's f of a times 1. The height of the second rectangle is f of a plus 1, so the area is f of a plus 1. And then so on, f of a plus 2 for the third one, and so on. So we just see that it's just the sum as n goes from a. So this should be n goes from a, not 1. It should be n goes from a to infinity of f of n. And, well, area under the curve is just the integral, right? So area under the curve is simply the integral from a to infinity of f of x dx. Okay, well, it's clear from the picture that area under the curve is smaller than area that's the sum of the areas of these rectangles. So just from the picture, we know that area under the curve is, we know that area under the curve is definitely smaller than or equal to sum of the areas of the red rectangles. Okay, well, what is this? Well, this is just integral. This side is just the integral from a to infinity of f of x dx. And this side, as we argued, the sum of the areas of the rectangles is just the sum. It's just the sum as n goes from a to infinity of f of n. And that's precisely this inequality here, 1. Inequality 1 is precisely this. So this is exactly inequality 1. So I'm going to put a check mark. So we proved it. Okay, so now we still have to prove the other inequality, inequality 2. And we do that by drawing a similar picture. So we draw a similar picture. Okay, so I draw my graph. So this is graph of f of x. So notice we're using that f of x is monotonically decreasing. F is monotonically decreasing. Very important for us to be able to infer from the picture. Okay, now this time I'm going to again plot my points. So I'm going to start at a, then I have a plus 1, then I have a plus 2, then I have a plus 3. Now I'm going to use different color, let's say pink. So now I'm going to draw rectangles, but, oops, sorry. Try to draw a little. So now I'm going to draw rectangles from the left-hand point. So this is going to be my first rectangle. This is going to be my second rectangle. It's going to be my third rectangle, and so on. Now, what are the areas of these rectangles? Well, like this one. This one has area f of, well, area of a rectangle is height times width. Now, sorry, I'll just label my axes. So this is my y, my x. So area of a rectangle is just height times width. Well, the widths are all just 1, so they're not going to play a role in the area. So it's just determined by the height. And the height of the first rectangle is determined by plugging it in the x value, a plus 1, into the function. So it's just a plus 1. And the area of the second rectangle is f of a plus 2, and area of the third rectangle is f of a plus 3. Okay, so let's keep that in mind. So from the picture, so let's write it this way. So we have sum, n goes from 1 to, not 1, but again, a to infinity of f of n. So remember, our goal is to prove this inequality, inequality 2, right? Which means I have to get an upper bound on f of n. So my inequality direction should be sort of this way, going. So I want an inequality of this type. So first I'm going to split it. So first I'm going to leave out the first term alone, f of a, and then plus sum as n goes from a plus 1 to infinity of f of n, right? Because these two are the same thing. Here I'm just adding up f of n as n goes from a to infinity, and here I'm just adding up from a plus 1 to infinity, except I have the f of a term out. But now, this sum here is just the sum here, f of a plus 1 plus f of a plus 2 plus f of a plus 3, and so on, right? It's just the sum of the areas of these pink rectangles. This is just the sum of the areas of the pink rectangles. Okay, well, certainly this is at most f of a plus area under the curve. For the function f of x, because the sum, so I didn't touch the f of a term, I left it as it is, and it's clear that the pink rectangles are an underestimate for the total area under the curve from a to infinity. So what is it that we get? Well, what we'll end up proving is that the sum, as n goes from a to infinity of f of n, we've shown that this is at most f of a plus area under the curve for the function, so that's exactly the integral from a to infinity of f of x dx. And that proves the inequality 2 that we claimed. Right? So this here, right here, is exactly the inequality 2 that we claimed here. So these two pictures kind of do the job. Okay, so integral test has been justified, and so we should see some examples of how to use it. Example. So let's use integral test to determine convergence / divergence of the series n goes from 1 to infinity of 1 over n to the p. So where p is some positive real number. Okay. So of course the answer is going to depend on p, right? So we're going to get an answer that says if p is in this range, then the series diverges. If p is in the other range, then the series converges. That's the kind of answer we want to obtain. Okay, well, if you want to apply the integral test for this series, we need to figure out what the function is. So for this series, n goes from 1 to infinity of 1 over n to the p. Well, it's of the form sum as n goes from 1 to infinity of f of n, where f is the function, f of x is the function 1 over x to the p, right? So note that f of x is continuous. It's a nice function on the interval 1 to infinity. It's positive. So f of x is has the right positivity property, and f of x is decreasing, is monotonically decreasing. So we can apply the ratio test. So not the ratio test. We can apply the integral test. Monotonically decreasing. So so we can apply. You must check these conditions before you can apply integral test. Okay, so the integral test tells us that in order to understand the convergence of the infinite series, it's enough to understand the convergence of the improper integral, the corresponding improper integral. So, but we already have done this in chapter, one of the chapters, chapter 7, I guess, on improper integrals. So note that we have already seen that the integral from 1 to infinity of 1 over x to the p dx, we know that this converges. If p is bigger than 1, and it diverges if p is less than or equal to 1. So the integral test lets us conclude that the same happens for the series. So we conclude that the same behavior happens for the series. So the sum, as n goes from 1 to infinity, of 1 over n to the p, this converges if p is bigger than 1, and it diverges if p is at most 1. And that concludes this problem. So let's use let's do another example. So use integral test to find out the convergence or divergence of the following series. N goes from, say, 3 to infinity of 1 over n times ln n. Again, so we note that the corresponding function is f of x equals to 1 over x times ln x, and this is continuous on the interval 3 to infinity, and it's positive, so f of x is positive, and it's decreasing. F of x is decreasing as x gets bigger and bigger, like f of x gets smaller and smaller because you're dividing. Which means that to understand whether or not this series converges or diverges, we have to understand whether or not the improper integral from 3 to infinity of 1 over x times ln x dx converges or diverges. We have to understand this integral. Okay. So to compute this integral, well, let's write down the definition. So this is limit as b goes to infinity, integral from 3 to b of 1 over x times ln x dx. Now I need to compute this integral, so let me do a side computation. So if I want to compute the antiderivative of x times ln x, I can use the u substitution. So u equals to ln x, then du becomes 1 over x dx, which is perfectly here. So this just becomes 1 over u du, and that because 1 over ln x is 1 over u, and dx over x becomes du, and this is ln absolute value plus c. That's what we get. Ln absolute value plus c, so this is just ln, well, u was ln x, so this is ln of ln x plus c. Okay, so going back here, we can now compute this integral. So we had limit as b goes to infinity of 3 to b of 1 over x ln x dx, and so we use fundamental theorem of calculus, so we have limit as b goes to infinity, antiderivative of 1 over x ln x, we just computed it, it's ln ln x, ln ln x. I don't have to write plus c because I'm computing a definite integral using fundamental theorem of calculus, so I just have to plug in the bounds, so I get limit as b goes to infinity of ln absolute value ln b. Now the absolute values won't play a role because I'm going to take a positive. I'm letting b go to infinity, so b is positive. So ln b is also positive. But in any case, so I have ln ln b minus ln ln 3. That's what I have. So again, this is just b goes to infinity of ln ln b. I can get rid of the absolute values because ln b is going to be positive as b gets larger and larger. And then minus ln ln 3. And this is going to be infinity because ln ln b part will grow larger and larger as b goes to infinity. So the answer to this integral is plus infinity. So the integral diverges. So what we have shown is that this limit as b goes to infinity from 3 to b of 1 over x ln x dx is plus infinity, so it diverges. So that shows that this improper integral here, right here, diverges. So the integral from 3 to infinity of 1 over x ln x dx diverges. Diverges, which implies by the integral test that the corresponding series must also diverge. That the corresponding series as n goes from 3 to infinity of 1 over n times ln n must also diverge. So using an integral, we were able to conclude the answer for the series. This is ln of n times ln n. Okay, the last thing I want to discuss in this lecture is the comparison test. So, okay, so suppose we have two series. We have two infinite series, and I have sum as n goes from 1 to infinity of a sub n, and sum as n goes from 1 to infinity of b sub n, such that the following condition holds. 0 is less than or equal to a n and less than or equal to b n. In other words, the terms, individual terms of the series, they're positive, and a n is smaller than b n. So what does the comparison test say? Well, it has two parts. The first part is that if you know that the sum as n goes from 1 to infinity of bn converges, then you can conclude that the sum as n goes from 1 to infinity of a sub n also converges. Also converges. Okay, so this makes sense because if the sum of the bn's converge, then the sum of the n's is even a smaller sum than the bn's, so it must also converge. And the second part of the test is that if the sum as n goes from 1 to infinity of a sub n diverges, then the sum of the bigger series also diverges. All right, this again should be evident because ANs are smaller than BNs. So if the sum of the series, of the sum of the terms for the smaller series is already infinity, then the same should be true for BNs, right? So we're using positivity here because the terms are all positive. The only way the sum of the ANs could diverge is if the sum of the ANs diverge to plus infinity. And so then the other one, the sum of the BNs is even bigger, so it must also diverge to plus infinity. So this shouldn't be too surprising because you've seen something similar to this for integrals when we talked about integral comparison. Okay, so let's do an example. So let's determine the convergence / divergence of the series n goes from 1 to infinity of 1 over n squared plus 7. Okay. So here's the solution. So let's note that the term we're interested in, the nth term of the series, is n squared plus 7. And that's definitely less than 1 over n squared, because I've made the denominator smaller. So 1 over n squared has a smaller denominator than 1 over n squared plus 7, so the fraction is bigger. And we know something about the other series. So we can compare the series that we're interested in to the series. So we compare our series to the other one. Our series is this one with series that correspond to n squared. Okay, but we know something about this series, right? We know that the series sum as n goes from 1 to infinity of 1 over n squared converges, because this corresponds to the case p equals to 2, which is bigger than 1. So we can conclude that the sum n goes from 1 to infinity of 1 over n squared plus 7 also converges, because it's even smaller, right? 1 over n squared plus 7 is even smaller than 1 over n squared. So if the corresponding series for 1 over n squared converges, then we can conclude that the series 1 over n squared plus 7 as n goes from 1 to infinity must also converge. So let me do one more example, and this is slightly more complicated. And this example is going to show you a nice trick that I think might be worth remembering. So again, let's try to determine convergence and divergence. Convergence or divergence of the following series. Sum as n goes from 1 to infinity of n squared plus 3n plus 1 divided by n cubed plus 5n squared plus 7n. So let me write a little better. So I have 5n squared plus 7n plus 11. Okay, so the intuition should be the following. The intuition, right? Intuition is the looking at the leading terms, right? So intuition, looking at the leading terms, the series looks like the nth an, which is the nth term, kind of looks like 1 over n, because it's n squared at the top that's leading, and n cubed at the bottom is leading. So it looks like 1 over n. N squared divided by n cubed is the same as 1 over n. So we know that we've got to compare it to 1 over n. So this is a good indication that we should compare it. We should compare somehow. Compare it to the series as n goes from 1 to infinity of 1 over n somehow. And if you can succeed doing this, then we're done, because this one we know diverges. This is the harmonic series. So this is the case of when p is equal to 1. And then we would be able to conclude that this also diverges. But how do we do the comparison? We can't just naively use comparison. So warning. So what would be so nice is to show that this term here is bigger than 1 over n, and then would be done. Because then, well, then we have something that's bigger than something that diverges, and then the thing we're interested in should also diverge. But warning is that this inequality, that would be so nice if it were to be true, this one. This would be so nice, because then we'd know that since this diverges, the sum of the series for 1 over n diverges, we would be able to conclude this diverges. But warning is that this inequality is actually false. So this is false. This inequality does not hold. Okay, so we can't use it. But there is a trick to compare it to 1 over n somehow. And the trick is to compare it to not to 1 over n, but to 1 over n times some constant. And here's how it works. So the correct way to proceed here is the following. So observe that the thing we're interested in is the nth term of the series we're interested in is n squared plus 3n plus 1 divided by n cubed plus 5n squared plus 7n plus 11. So I want to be able to show that this is greater than something that diverges, because then I know that this thing diverges. Okay, so here's the trick. So first, I'm just going to ignore the rest of the terms in the numerator. So certainly, this is bigger than n squared divided by n cubed plus 5n squared plus 7n plus 11. Right? Now, I have to do something with the denominator. So first inequality was true because I just made the numerator smaller by ignoring these two terms. Now, to keep going, I need to make the denominator bigger because I need to get something that's overall smaller, which means I have to make the denominator bigger. So here's a trick. So here's what you can do. You can just make the denominator bigger by making every term n cubed. So first is n cubed. Here, I didn't touch this term. So instead of writing 5n squared, just write 5n cubed. Right? So instead of writing 7n, just write 7n cubed. Instead of writing 11, write 11n cubed. So going from here to here is fine because here we made the denominator bigger. And so overall fraction here was smaller than this one. We made the denominator bigger. So the fraction got smaller. And this is nice because it's easier to add these terms, right? You can combine them. So this is equal to n squared divided by, well, you just have apple plus 5 apples plus 7 apples plus 11 apples. So how many apples do you get? So I have 6 plus 7, 13 plus 11, 24. So I have 24n cubed. Okay. That's perfect. So now this is n squared divided by 24n cubed is the same thing as 1 over 24 times n. So we were able to compare it to not 1 over n, but 1 over 24 times n. But this is just a constant. It's not going to matter, right? So thus we've shown that n squared plus 3n plus 1 divided by n cubed plus 5n squared plus 7n plus 11 is bigger than or equal to 1 over 24 n. Well, this is just 1 over 24 times 1 over n, right? This is just a scaled version of 1 over n. Well, since we know that the sum n goes from 1 to infinity of 1 over 24 times n, so 1 over 24 times 1 over n, well, this is just, you can just pull the 1 over 24 out. Sum as n goes from 1 to infinity of 1 over n diverges, because this, well, this is the harmonic series. This is the case when p is equal to 1. We conclude that the series that correspond to the bigger nth term must also diverge. So by comparison test, the other series, the bigger series, n squared plus 3n plus 1 divided by n cubed plus 5n squared plus 7n plus 11 also diverges. And this concludes lecture 22.